Dear students, in physics, now we have come to another practical in the section heat. So, what we are going to see in this experiment, you can see here, determination of the specific latent heat of vaporization of water by the method of mixtures. I'll show you what we are going to do here. First, let's try to understand the setup and try to understand the theory, and then we will go into the steps. Okay. Now look at this. This is the setup we are going to do. Let's try to understand few of these arrangements or the equipments. Look at this one. This is what we call steam generator. What do we do there? We fill it with some water and then we boil it, right? So water gets heated. When it reaches 100 degree, it boils. We studied that, right? Under normal atmospheric pressure, it gets boiled at 100 degrees centigrade. We call it the boiling point. But if the pressure changes, if pressure increases, then it will not boil at 100 degree. It boils at a different temperature. Usually, when pressure increases, boiling point also increases. When pressure decreases, boiling point decreases. So in one atmospheric pressure, if it is boiling at 100 degree, let's say you take that water to the top of a mountain, which is so many meters, thousands of meters above the sea level, where the pressure is going to be less. When you go higher and higher from the sea level, pressure drops. When the atmospheric pressure is less, boiling point also will be less. It doesn't have to be heated up to 100 degree. Maybe at 90 degree itself, it starts boiling. The vaporization happens at 90-95 degrees. So understand, pressure and boiling point are related, right? We usually assume 1 atmospheric pressure, 1 Pascal, and at that pressure, it's 100 degree centigrade, right? Coming back here, so what do we do here? We fill this with water. This is a thermometer, that you know that, thermometer to measure the temperature. And you can see this is the opening to get the steam out. From this only the steam is going to come. And look at this one. Here we have kept another tube. What's the purpose of this tube? Often they ask, if this experiment comes in the exam, often they ask some question about this tube. What is the purpose of this tube? Why do we need that tube? Listen carefully. Now, what will happen if I did not have this tube? This is my steam generator. This is the opening to get the steam out. Right. Let's say it's closed. Only the thermometer is kept. Now, what will happen when you boil it, when you heat it? Suppose if this side gets blocked. Suppose the steam is not able to get out of it. Why? A lot of steam will be generated. It comes through this way and it's very close to this surface, right? So there might be, like, when more and more steam comes out, there might be a bit of a rush, right? The space may not be enough to release all the steam out. Then what will happen? More and more steam will get congested here. When more steam is congested, that's why we call the pressure increases. Internal pressure within this container, within this steam generator, will increase. What is wrong when the pressure increases? There are 2 problems. Problem number 1, when pressure changes, when pressure increases, boiling point will change. Now it won't be at 100 degree, it will boil at a different temperature. So initially started boiling at 100 degree. So initial steam was coming at 100 degree. Now the pressure started increasing. Pressure is high. So the boiling point is also going to be high. Now the boiling point may not be 100 degree. Problem number 1. When the pressure increases, the boiling point will change. So you cannot assume that the steam is at 100 degree. Second, It's risk. Because when water changes its state to steam, it expands rapidly. Huge expansion of volume happens. So if there is no space, the pressure keeps increasing. At some point, there is a possibility of that cracking. It can blast. I'll tell you an example. There are these factories which use these boilers, big scale boilers. Now these are small ones where we use like half a liter of water and we boil it. But there are boilers where we use thousands of liters of water and we boil it for industrial purposes. For example, when in the pasteurization factories or in some other food processing factories, they might have steam lines, right? Silver or aluminum lines through which steam goes to maintain the heat. So where do they get the steam from? They will have boilers. Boilers send the steam, or sometimes hot water also. So what will happen when the water gets boiled, when it's heated, it evaporates, it becomes vaporized steam, it takes a lot of space. Suppose if the exit ways are blocked, all the steam is going to get congested within the boiler. Pressure increases rapidly and boiler will blast after a point if it doesn't have the proper safety measures, right? If the safety measures malfunction, then the boiler can blast. And there are incidents like that all around the world where boilers blast, where the boiler operator gets injured. There are incidents where even boiler operator has had to lose his life because of the blasting of boilers, right? So you have to be safe here. This tube ensures that. Well, how does that tube ensure? When more and more steam gets accumulated here, if the pressure increases, then this water will start rising, go up in this water, in this tube. That the water level within the tube will start rising. It will go up. So that water takes space through the tube, leaving more space for the steam within the steam generator, such that pressure is maintained. You heat it more and more. We can do the experiment. When we are doing the experiment, if we block this side, you can see suddenly the water will come out of this. It will start coming out from this tube. Why does that happen? So that the internal pressure is maintained at the atmospheric pressure itself. Right. So what's the purpose of this tube? There are two reasons: to maintain the pressure, for safety reasons. Notice another thing. This tube has to go until it touches the water. That means this end of the tube has to be within the water level. Why? If you keep it above the water level, all the steam generated would go through this tube and you will not get much steam coming onto the other side. So make sure you submerge that one end of the tube into the water. Otherwise, the purpose is lost. You will not get the steam. Right? This is how you get the steam out. And this is the tripod. You know, we keep the burner, Bunsen burner, and we keep a tripod. On top of the tripod, we keep a wire mesh. On top of the wire mesh only, we keep whatever we want to heat, and we heat it. Here we keep an insulator, heat insulating sheet, right? Usually we keep Regifoam or asbestos sheet here. Why do we keep that? Because the heat from this burner should not be transferred to the other side. This is where we are measuring the temperature and all that. So this heat should not be transferred here. For that, you keep this asbestos sheet, or you can keep a Regifoam, whatever. A thermal insulator has to be kept in between. Okay? Because guys, increasing the distance from this point to few meters is impossible. Because if you keep the distance from here to here as few meters, by the time steam reaches here, most of it would have condensed into water again. So you can't increase the distance between those two. You have to keep it close so that all the steam goes as steam itself. Still, we can't transfer the heat to the other side. So keep an insulator, thermal insulator in the middle. Right. Then understand what this is. This is what we call steam trap. The steam trap, you can see when the steam goes from here. Imagine if I don't have this steam trap, what will happen? This is my calorimeter and water. This is the tube that brings the steam. when steam enters here and by the time it reaches here, some part of the steam, right, some part of the steam would have condensed into water within this tube itself, within that tube itself, right? Whereas I don't want condensed water to fall in here. Why? First, let's understand what we are trying to find here. We are trying to find specific latent heat of vaporization. What is the meaning of latent heat of vaporization? See, you take water in the room temperature. Let's say room temperature is 30 degrees. You take a glass of water at 30 degrees and let's say you start heating it. So 30 degree becomes 40, 50, 60, 70, 80, 90. It goes up like that. And the water reaches 100 degree. At 100 degree only you see all the bubbles start coming out and we call it boiling. At 100 degree, when the water reaches 100 degree, it will remain at 100 degree. When you give more heat, the water at 100 degree changes its state to vapor. Liquid changes into vapor. What is the temperature of liquid? 100 degree. What is the temperature of vapor? That is also 100 degree. 100 degree water changes into 100 degree vapor. Just the change of state, For the change of state, it needs heat. From water to vapor, when it changes the state, it takes some heat. It consumes some heat for that. That is what you call latent heat of vaporization. Similarly, when from solid to liquid, when the change of state happens, at that point also it consumes some heat without change of temperature. For example, 0 degree ice cube changes into 0 degree water. Temperature is same, but change of state happened and it has consumed some heat for that, which we call latent heat of fusion, which we have seen in another practical. So here what we see, 100 degree water. So understand, after heating it to 100 degree, if you don't give further heat, it will remain at 100 degree. Let's say it's a fully insulated box, insulated container, you heat it to 100 degree, right? It became 100 degree water. Now you stopped giving the heat, the water will remain at 100 degree. That's what we try to do. See, what we do, we heat the water at home, we boil the water. When we see the steam coming out from the kettle, if you are using a kettle, from the kettle the steam will come out. At that point, what we do, we switch off the kettle, we take the water, put it in a flask, thermal flask, and keep it. So what we have done, 100 degree temperature water, we kept it in the flask and we keep it. So next few hours, it remains at 100 degree, but there will be a small heat leakage, right? Thermal flask, 90% it might prevent the heat transfer, but still there might be a small amount of heat. So it wouldn't remain at 100 degree forever, but that's what we are trying to do. So 100 degree water is there, remember that. When you give further heat only, it changes to steam. Some students have a wrong understanding. They think after 99 degree water, it's 100 degree steam only. No. 100 degree water is possible. 100 degree water is available. And when you give more heat only, it becomes vapor. So how much of heat it consumes from 100 degree water to 100 degree vapor, to change the state from 100 degree liquid to 100 degree vapor, is what we call the specific latent heat of that water, that liquid. Clear? Right. Similarly, see, now I was talking about water becoming vapor. Similarly, when vapor becomes water, steam is condensing into water. 100 degree steam changes to 100 degree water. It releases heat. 100 degree steam changes to 100 degree water. No change in the temperature. 100 degree steam, 100 degree water. Both at 100 degree. Only change of state happened. From vapor, it changed to liquid. Then it releases the same amount of heat as it consumed, the same amount of heat that it consumed when it changed from liquid to vapor. That same amount of heat it will release when it changes back from vapor to liquid. Right? Latent heat of vaporization. That's what we are trying to do here. So what we are going to do here, we take the steam from here, put the steam into this water. So what will happen when steam continuously goes in? Let's say M is the amount of steam that you have put in here. First 100 degree M, 100 degree steam changes into 100 degree water. It releases some heat, which is M into L. That's the latent heat released by M kilograms of water. Then imagine this water was initially, let's say it was at 25 degree. After you have finished all this, it went up to 35 degree. That means you are going to send the steam into the water continuously. You do it for a few minutes and you stop it. Now it has gone to 35 degree, which means you will be stirring it as well. Why stirring it? To ensure that all the water is at the same uniform temperature. Right? All the parts of water within this container. So 100 degree water, now 100 degree steam has become 100 degree water, but finally when it is at equilibrium, it is at 35 degree, right? So this M, now this was steam, that has become water, same M, that has become water, but 100 degree water. After releasing the latent heat, it becomes water at the same temperature. 100 degrees, it's water. But at the end, it is also at 35 degrees. MC 100 minus 35. From 100 degrees, when it changes to 35 degrees, it must have released some water. From 100 degrees, when it changes to 35 degrees, it must have released some heat. It must have released some heat. MC theta, MC delta theta. MC delta theta. From 100 degree, it has come down to 35 degrees. MC delta theta. This is the total heat released by the vapor. Vapor becoming water, and then the water coming down to 35 degrees. Who gained this heat released by these? Who got that heat? Who gained that heat? This calorimeter and the stirrer. Usually calorimeter and stirrer are copper or aluminium. Let's say it's copper, right? Then let me call it as MC, CC, copper, C for copper. Theta, they were at 25, they went up to 35. So this is the amount of heat calorimeter and the stirrer have gained. Steam lost the heat, calorimeter and stirrer gained. Not only the calorimeter and stirrer, water also must have gained heat. Why? Water initially at 25, it has gone up to 35. MW, CW, 35 minus 25. So heat released by steam has been gained by water and the calorimeter plus stirrer. We make an assumption there is no loss to the environment. Understand? Right. So now come again. I told you when we transfer the steam from here to here, I want pure steam. We call it dry steam, dry vapor. There shouldn't be any water mixed with that. Why? We assume all the additional mass drops here releases latent heat. All the additional mass that falls into this releases latent heat. That means it has to be vapor only, because vapor, when it changes to liquid only, it's going to release the latent heat. Suppose if you have already got some water here, that means the water, the vapor which already condensed into water, if that falls here, that water will not release latent heat, right? But you are going to capture that in the additional mass, right? You get what I say? So therefore, we have to ensure whatever that falls from here has to be steam and steam only. There is no water that should be falling into this, because we assume it's only steam, and every gram you are getting there will first release the latent heat. Then only it changes to water. Then it releases heat to come down to 35 degree. Clear? Right. So how do we do it? We use this steam trap. Can you see? all the vapor will come here, but some part of vapor might have condensed here itself. So it will fall as water here. Vapor and water will fall in. It falls into this trap, this small apparatus, where we have another tube which is bent like this. Can you see? It's bent like this. So what will happen? Only the vapor will have the opportunity to go through this. Water, where would be the water? Water would be here. Water would be here. Understand? Water will not be able to go through that. Clear? So we call it steam trap. That means, what is the purpose of steam trap? To trap the water which is already condensed. It releases only the steam, dry steam. We can ensure the calorimeter and water receives only steam. Then the stirrer is there. Why do we have the stirrer? When the steam falls here, the surface temperature might increase. Top part of water, the water here might be increasing the temperature, whereas the bottom part of water might be remaining at a low temperature. The temperature might not be uniform within the calorimeter. So you keep mixing it, stirring it. The hot water, cold water, everything you keep stirring it so that uniform temperature is always maintained within this calorimeter. Then only I can assume whatever the reading I get on the thermometer, I can assume that is the temperature of everything, because the temperature has to be uniform. If you have different temperature at the top, different temperature at the bottom, then the thermometer reading is going to be different, right? That is not a good representation of all the water's temperature. Clear? So make sure you keep stirring it continuously. And also have a look at the calorimeter we are using. See, there will be a gap here. This gap might be either insulator or vacuum. Why? So that the heat conduction is prevented. Heat conduction. Also, we will be using silver coated or copper coated shiny surfaces, because radiation will be prevented. If you use shiny surface, radiation can be prevented. Also, we usually close this and do the experiment, but here, since we have to put the steam in, we can't close it. By closing it, what we do? We prevent the convection. Why do we prevent convection, conduction and radiation? So that there is no heat transfer to the environment. Why? You are taking an assumption. All the heat lost by the steam has been gained by water and the calorimeter plus stirrer. So if there will be some additional loss to the environment, then this assumption will be wrong. And it's very difficult to measure the loss to the environment as well. Understand? So we are taking all the efforts to ensure no heat loss happens with the environment. Or you are not gaining any heat. Suppose if the temperature here is lower than the environment, you might even get the heat from the environment. Whichever the way, it's an error in the experiment. Whether the system gives heat to the environment or the system gains heat from the environment, whichever it is an error. We are trying to prevent that error. Clear? That is what the arrangement is all about. See again, Bunsen burner, tripod, there will be a wire mesh here. Then we keep the steam generator. So there is one more thing, the steam generator we are going to use will have a handle like part here, where this part will be transparent. That will be a transparent part. What is the advantage? When you fill this with water, we can see where the water level is. So if we know where the water level is, then when you are putting this tube inside, you can judge whether the tube has touched the water or not. Because of that, we may have a handle-like part with this steam generator, where it's a transparent part which will show us where the water level is. Clear? The concept. In the experiment referred to above, let the mass of the empty calorimeter with the stirrer M1. M1 is the empty calorimeter plus stirrer's mass. Mass of the calorimeter with water. We let's say MC, calorimeter plus stirrer's mass. This is MC plus MW. After filling this with water, you again get the mass, which is MC plus MW. Initial temperature of the water is theta 1. Maximum temperature of the water after mixing with the steam is theta 2. What is the meaning of maximum? Listen to me. you keep adding the steam, right? Let's say you started at 25. Now you look at the, you are keeping adding and mixing it. Now you look at the thermometer, say it has come to 35 degrees. Now you remove the steam. Can I take the temperature as 35? No. Listen why. The temperature, the thermometer bottom is here. You are sending the steam here. Suddenly you stop it. Fine. Still you have to keep stirring it for some more minutes to see whether any changes happen, because sometimes still you might have had some more hot water here. This point would have been at 35, this might have been at 37 sometimes. So when you keep mixing it, right, they all together might go further up to 36 degrees. So which one do I take as end temperature? After you remove the steam, still keep stirring it and look at the thermometer. Thermometer temperature reading will go up, up, up. After a point, now you have removed the steam, still it is going up. After a point, still when you are stirring it, it stabilizes and then it will fall down. It will remain stabilized for like 2-3 minutes and then it will start falling down. Why it falls? However you have insulated, there will be some heat leakage to the environment. So it loses heat to the environment. Because of that, the temperature will fall. Right. So you have to find where it goes to the maximum and where it stabilizes. That is what we take as the end temperature. End temperature. That's why it says maximum temperature of the water after mixing with the steam, theta 2. Mass of the calorimeter with mixture, M3. That means this is MC, MW plus M steam. Some steam has condensed into that and it is also mixed with the water now, which you can't differentiate, but will have more weight now. MC, MW, MS. Specific heat capacity of calorimeter and metal C1, or we can take it as CC because we use a copper one here. Specific heat capacity of water is CW. Specific latent heat of vaporization of water is L. Then assuming no loss of heat to the surroundings, heat lost by steam is heat gained by calorimeter and water. This is the equation I wrote earlier. M3 minus M2L. M3 minus M2 is the steam. M3 minus M2 means the difference between these two is the mass of steam. So mass of steam into L gives us the latent heat released by steam when it changed the state into water. And then that water from 100 degree, it comes down to theta 2, the end temperature, end equilibrium temperature. That's the total heat lost. And then gained M1C1. M1C1 means the M1 is what? Calorimeter and stirrer together. C1 is their specific heat capacity. M2 minus M1 is the water, mass of water, and water which was already there, CW. All these have increased from theta 1 to theta 2. Multiply, assuming there is no loss to the environment, then you know everything other than L. This is what you don't know. Everything else you have read from the experiment. C1 is, if you are using a copper calorimeter and stirrer, we usually assume C to be around 400. You can use 400. Water specific heat capacity is considered to be 4,200. 4,200. You can substitute those values which we studied in the theory as well and find L. Understand? This is what the concept is. Now look at this graph with time in seconds, how the temperature changes. How the temperature changes, I'll show you. Look at this part. So what is this? At this point, it is steam. At this point, it is water. Still at 100 degree. Still at 100 degree. This will be 100 degree. 100 degree steam is what we got. That steam hits the water surface. First, it converts or changes the state into liquid. So initially 100 degree remains the same. After it has changed to water, this is water at 100 degree, right? Then the water loses its temperature. This will be water at theta 2, the end temperature. Understand? At the same time, what is this? This is calorimeter plus water at theta 1. They increase the temperature. Calorimeter plus water at theta 2. Clear? So this shows the heat loss. I mean, the temperature changes, and that's the substance that loses heat, whereas these are the substances that gain that heat. Clear? Method, very simple. Look at this. Measure the mass M1 of the calorimeter with stirrer. Fill about 2/3 of the calorimeter with water at room temperature and measure the mass M2 again and the temperature theta 1 of the water. Temperature theta 1 of the water. Arrange the steam generator to supply continuous stream of steam. Obtain dry steam after passing through the trap and allow the steam to strike the surface of water in the calorimeter. Stir the mixture well, and after its temperature has risen by about 10 degrees, stop mixing steam. After stirring to reach the maximum temperature, note down the temperature and finally measure the mass of the calorimeter with its contents. Right, so this is what I explained now. So now we understand the concept, we understand how the arrangement has to be, right? So let's see what are the apparatus and materials required for this. A calorimeter, a stirrer, 2 thermometers, a steam generator. Why do we need 2 thermometers? One is to be kept within the steam generator just to ensure it's 100 degree, because sometimes the pressure is different. It can be at a different temperature as well, right? The boiling. So to ensure to check the boiling point temperature, we keep one thermometer there and the other thermometer within the calorimeter where we are going to mix the water and steam. The temperature, the thermometer you keep within the calorimeter can be even 0 to 50 degree thermometer, because once they asked, they gave 2 thermometers, AB. A was 0 to 100 degree thermometer, B was 0 to 50 degree thermometer. That means the maximum scale you have is up to 50. They asked which one would you keep in the calorimeter. So you need 0 to 100 degree in the steam generator, because steam generator is going to be, the temperature is going to be around 100 degree. 0 to 50 wouldn't help you there. So you have to keep 0 to 100 degree in the steam generator. If the other one is only 0 to 50, you can use that in the calorimeter with water where you're going to mix the steam. 2 thermometers, a steam generator, a steam trap. Steam trap, there have been several questions about that in the exam, so be familiar with that. Steam trap, this is how steam comes in. You have a curved tube like this. Understand, right? This is where steam in, steam out. The funny thing is, sometimes students know from where to give the steam in. Sometimes they draw steam in from here, steam out. Make sure you keep it open, don't close it, right? There is another way of a steam trap. Even this is fine, right? If it is not a curved end, they should not be aligned at the same line. So suppose if water drops fall, it will fall here and it will remain here. Steam would come through this, steam in, steam out. Whichever is available in your lab, you can use it. If they ask you to draw, whichever the way you can draw it, it's fine. Steam trap. A chemical balance to measure the mass, an insulating sheet that is to keep in between the burner and the calorimeter, a Bunsen burner, a tripod and a wire mesh, right? That's all the apparatus. Now let's see how we are going to do this experiment and what readings we are getting. We will see it now. Dear students, in physics, in the section heat, the next experiment we are going to see is about finding the latent heat of vaporization of water. You know, water we can heat it up to 100 degree. When it reaches 100 degree, then it becomes vapor. From 100 degree water, that means in the liquid state, it can be at 100 degree. Then it changes to 100 degree vaporized state. Both are at 100 degrees, 100 degree water, 100 degree vapor. The 100 degree water, for it to reach 100 degree vapor state, it needs more heat to be absorbed, which is what we call specific latent heat of vaporization of water. How to find that is what we are going to do in this experiment. The method we are using here, we call it the method of mixtures. Using method of mixtures, finding specific latent heat of vaporization of water. That is what the experiment is. The experiment is very simple. We are going to take water in a calorimeter, and then we will first measure the temperature. Then we will continuously send vapor at 100 degrees into that water. So what will happen to the water? The temperature of water and calorimeter will increase. After a certain point, we will stop sending the vapor into that. We will find the temperature increase, and we will do the calculation like this. The vapor that reaches the water surface, first it changes the state. From the vapor state, it changes to a liquid state. When it changes the state, it releases the latent heat. From 100 degree vapor, it changes to 100 degree water. Latent heat is released. Plus the 100 degree water continues to cool down, and it will reach an equilibrium of heat equilibrium. Which means, let's say the equilibrium is at 35 degree. From 100 degree, the water goes down to 35 degree. Which water? The water that has come from the condensation of steam or vapor. So vapor, when it changes its state to water, the liquid state, it releases heat. That water continues to cool down. That means it continues to release heat. Those heat that has been released from this will be absorbed by the calorimeter and the water which was already in the calorimeter. So calorimeter and water temperature increases, right? The released heat and the absorbed heat must be equal. Using this method, we can find out the specific latent heat of vaporization of water. This is what we call the method of mixtures. First, we will see what materials and apparatus are required to do this experiment. So when you look at the materials and apparatus required for this experiment, this is the first one. We need a steam generator. You call it steam generator. What we do, we fill this with water. Here you can see the level of water. See, when you fill this with water, you can find the level of water through this, and the steam will be generated, and it will be coming out from this one, right? We have kept a tube here. When I do the experiment, I will show you why we have kept this tube. The usefulness of this tube I will explain while the practical is in progress. This is the tripod and a wire mesh. This is the Bunsen burner. On that only we are going to keep this and boil the water to generate steam. And then you can see this is what we call the steam trap. Steam trap. What this does is, you can see, there is a tube inside. Within this tube, there is a tube inside. Can you see that? So what will happen when the tube comes out, when the steam comes out from this steam generator, sometimes when it goes through this tube, part of the steam might get condensed, and it might turn into, the steam might turn into water. For our experiment to be precise, the dry steam has to be sent inside the water. The water that condenses from the steam should not fall into the calorimeter and water. So this tube helps us to make sure only the steam passes through this. Within this tube, if any part of steam has condensed, and if the steam has changed into liquid state, that liquid will be trapped here. See, within this part, the liquid will be trapped. Only the steam will go through this. Students must clearly understand when this steam trap is given, which side is for steam input and which side is for steam output. Understand where this internal tube is connected, that is where you get the steam output. Then only the water will be trapped here. Suppose if we use it other way around, if you keep it like this, and if steam goes in from here, the condensed water will not be trapped. Can you see? It will go through this. So you can't use it the other way around. You have to make sure this is how you fix it. The steam input should come from this side, and where this internal tube is there, that is for the steam output. This instrument, we call it the steam trap. Understand? So often they ask this in the exams, what is the usefulness of using this steam trap? So you have to mention there, it is to ensure only the steam goes into the water. If any part of steam has already condensed, if it has become water, that should not be dropped into the calorimeter with water. This ensures that. Then the other apparatus we need, you need a thermometer to measure the temperature. And this is the calorimeter with a stirrer, because we have to keep stirring it until the equilibrium is reached. And then the insulator. See, this is another bigger calorimeter with insulator. So what will happen? We will keep this calorimeter. This is where we are going to have the water. We will keep this inside the insulated calorimeter so that the heat loss to the environment is minimized. Heat loss to the environment or heat absorption from the environment is minimized. We have water, a beaker of water. This is to generate steam. We will be filling this steam generator with this water. And then we have a 3-beam balance or 3-beam scale. This is to get the weight of calorimeter with water. To measure the weight, we will be using this 3-beam scale. If you have an electronic scale, you can use the electronic scale also. But electronic scale is quite easy. You just keep anything on top of that and you read the measurement. But you have to be familiar with a 3-beam or 4-beam scale as well. Here I am using a 3-beam scale. That's all the apparatus required to do this experiment. What is going to be the first step we are going to do? First, we will measure the weight of the calorimeter with the stirrer. Then we will fill water in it and we will start the experiment from that. Right, we will measure the calorimeter with the stirrer. Make sure you get the measurement with the stirrer, right? Let's increase this to 100. No, it's less than 100. Let me increase 10 by 10. It's more than 20. See, at 40 it has fallen down. That means it must be above 30 but below 40 grams. Let's bring it back to 30. Let's increase one by one now. We have to make sure the line here tallies with 0. Yes, we get 37.8 gram the reading. 37.8 gram is the weight of calorimeter with the stirrer. Shall we write this in a table? Let's write down all the readings in a table like we usually do. At the end, we can do the calculation. So, the mass of calorimeter and the stirrer is 37.8 grams. So, MC is 37.8 grams. Let's write it here. Next, what do we have to do? We have to fill the calorimeter with water. Usually, we fill it up to 3/4 of the calorimeter. So, let's fill it up to 3/4 of the calorimeter and get the measurement, get the weight of it. All right, students, now understand what we are going to do next. First, we will fill this steam generator with water and we will let it boil and generate steam. Meanwhile, let's fill the calorimeter with water. Usually, as I told you earlier, we fill it 3/4 of it with water. There will be one error in this experiment. If you start the experiment, if you start the temperature of calorimeter and water initially at the room temperature, when the steam is passed on to it, the temperature will keep increasing. Compared to the environmental temperature, compared to the room temperature, temperature of this calorimeter and water will keep increasing. Then what will happen from the calorimeter and water, there will be heat lost to the environment. However, we have insulated, we cannot prevent 100% the heat loss to the environment. So what we are going to do, we are going to do a correction for this. We can't 100% prevent it, but we can do a correction for it. The correction is this. From the room temperature, let's start the experiment 5 or 6 degrees less. Suppose if room temperature is 30 degree, we will start at 25. How do we start at 25? Either you can take cool water. If not, you take water, mix few ice cubes into that and bring it down 5 degrees less than the room temperature. Then you start passing on the steam to it. Then what will happen? The temperature of that will increase from 25. If room temperature is 30, from 25 to 30 when it is increasing the temperature of calorimeter and water is less than the environmental temperature. So what will happen? The calorimeter will obtain heat from the environment, that is from 25 to 30. So what we will do, if room temperature is 30, we will start at 25, we will go up to 35 and finish it. So 25 to 30, it gains heat from the environment. Then when it goes above the room temperature, that means 30 to 35, in that 5 degrees gap, the temperature of calorimeter is going to be more than the environment, then it will lose heat to the environment. So the correction we are doing here, in the first 5 degrees, when it is below the room temperature, it gets heat from the environment. When it is above the room temperature, it loses heat to the environment. We can make an assumption the heat it gained and the heat it has lost will be equal. This is a correction we are doing. Therefore, we have to start the experiment with 5 or 6 degrees less than the room temperature. Right. Anyway, first let's fill this steam generator with water and let's give it time to generate heat. When I am filling the water, you can check the level of water in the transparent tube. You can see this is where we check the water level. Yes. See, the water level is going up. Right, I am keeping the water level somewhere at this point. Why does it matter? Why do I have to know about the water level? Did you see this tube? When I close this steam generator, we don't close it completely, we keep this tube. And the tube also must touch this water level, it must, the other end of the tube must be within the water. Shall we double check that? See, when I am closing it like this, it goes up to here. See, it goes up to here, whereas the water level is here. Why do we do that? You know, when the water boils, it generates steam. From the liquid state, when it goes to the vapor state, it expands. It takes more space. So when it takes more space, if I have just kept it closed, the pressure within the steam generator will increase. When the pressure increases, we cannot assume the temperature of steam is 100 degrees. Usually at the environmental temperature, we assume it to be 100, the boiling point, we assume it to be 100 degrees. But the boiling point will not be 100 degree if the pressure is higher. So what do? We keep this tube. What will happen when the pressure increases? When steam is generated and steam captures the space, the pressure increases, then the water, since it needs more space, it will come up in this tube, so that the internal pressure is maintained at the room temperature, environmental pressure itself. Understand? So we keep this tube, make sure the tube is within the water. Why do we keep this tube? It ensures the pressure is maintained at the environmental pressure. Right. Now I have filled it, let's fix it and keep it to boil. While that is being boiled, let's measure the room temperature and let's get the water 5 or 6 degrees less than the room temperature. Then we have to measure the weight of that as well. Let's check that. Students, you can see here the room temperature is 28 degrees. 28 degrees. You can see that here, room temperature 28 degrees centigrades. So we can start the experiment 5 or 6 degrees less than 28, maybe at 23 or 22 degrees we can start the experiment. That means the temperature initially can be set at 22 or 23, and then we can finish the end of the experiment. We can try to achieve the temperature 5 or 6 degrees above the room temperature. So we will start at 23 and we will try to finish it at 33 because the room temperature is 28 degrees, right? Let's fill this with water. After I fill this with water and ice cube, approximately 3/4 of the calorimeter must be filled with water. Let the ice cube melt. Once it is melt, we can check the temperature. I am planning to start the experiment with 23 degrees. In case if it has gone below 23, we may have to wait until it reaches 23. Sharp when it is at 23, we will start sending steam into it. Let's add more ice cubes. Students, now it is at 22 degrees, right? So we will wait until it becomes 23. You can see here it's 20. You can see here it's 22 degrees, right? So now we will get the weight of this. We'll measure the weight of this, and then we will wait until it becomes 23. And once it is 23, let's keep it within the insulated calorimeter and start sending the steam through it. Let's measure the weight of calorimeter with water and stirrer in it. Make sure when you get the weight of this, since the temperature is less than the room temperature, there might be mist around this. On the outer surface of this calorimeter, there might be mist. Make sure you wipe it, right? There is no mist or there is no water on it. Make sure it's clean. Right. Now let's get the weight. Let's bring everything to 0. Right. It's more than 100, but less than 200. So let's keep it at 100. Let's increase 10 by 10. Seems more than 20, but less than 30. See, when it is at 30, it falls down. Now let's increase 1 by 1. We get a weight of 124.1 gram. That is calorimeter, the stirrer and the water together. It's 124.1 grams. Let's note it down in our table. So the mass of calorimeter and water is 124.1 grams. Let's note it down. 0.1 gram. Now what do we have to do? Let's generate the steam. Let the steam strike on the surface of this water. Let the temperature increase by approximately 10 degrees. And then we will measure the weight of the final calorimeter with water. Right? So let's see how to send the steam into the water now. Students, you can see the steam is being generated. We can see the steam coming out from this. There is one more thing you have to note here. The steam should be dry when it is striking the surface of water. These water drops should not fall into the surface of water, because we assume a dry flow of steam strikes the water. So what you have to do every time when a water drop forms here, you just have to wipe it and ensure only the dry steam falls into the water, right? Let's keep this calorimeter with water within the insulated calorimeter. Let's check the temperature again. You can see now the temperature is 23 degrees. Now let's turn this steam trap so that the steam directly strikes the surface of water. We have to make sure the water doesn't fall into that. Keep stirring it to ensure uniform temperature within the water. We have to continue this until we reach a temperature around 33 degrees. It has gone up to around 28 now. Let's wait until it's approximately 33. Now it's close to 33. Check the temperature now. You have to keep stirring it to ensure the maximum temperature that the water reaches is 33. Because what we need to check here, what we need to note down here is the maximum temperature that it goes to. Now it has reached 33. It has gone to 34 degrees. Can you see? It has gone to 34 degrees. So we can assume the maximum temperature that the water has reached is 34 degrees. You can see here 34 degrees. 34 degrees. So let's write this down also in our table. Initial temperature was 23 degree. After the steam supply was given, it increased up to 34 degree. Let's write it down on our table. So the room temperature was at 28 degree. Initial temperature of water and calorimeter 23, and the final temperature was 34 degrees. Now let's measure the final weight of calorimeter and water. The water now is going to include the water that we initially had within the calorimeter plus the water that came through the steam. When the steam condensed, that would have generated, that would have given some more water. So all the water together plus calorimeter and stirrer will get the weight now. Let's see what is the final weight of this calorimeter and water. We get 125.7 grams, 125.7 grams, that's the final weight of it. So from this we can calculate how much of steam has come into this water. Then as I mentioned earlier, the heat released by steam and the water is equal to the heat obtained by the calorimeter and the water which was already within the calorimeter. By equating these two, we should be able to find the specific latent heat of the vaporization of water. First, let's write this down, 125.7 grams. The total weight is 125.7 grams. If we get the difference between this 125.7 and 124.1, that is 1.6 grams, that is the weight of steam, the steam that has come into this water. That 1.6 gram of steam would have condensed into water, and that water from 100 degree it has come down to 34 degree. So when the state change happens, steam changes into liquid, latent heat would have been released. Then the liquid, the water at 100 degree, when it comes down to 34 degree, it releases heat. So both those amounts of heat released will be gained by calorimeter, stirrer, and the water which was already within that, which was at 23 degrees at the beginning, right? So when they obtain that heat, the temperature has increased from 23 to 34. By 11 degrees it has increased. Now we can equate these two. The heat released by the steam and the hot water is equal to the heat obtained by the calorimeter, stirrer, and the water which was already there. By equating these two, we can do the calculation and find the specific latent heat of vaporization of water. Let's see how we can do that calculation. Students, you can see the readings we have got here, readings and calculations. MC, MC plus MW, theta R, theta 1, theta. Let me call this as M1, M2, M3. It's easy to write like that in the equations. So, you know, M steam is going to be M3 minus M2, right? M water, the water which was already there is going to be M2 minus M1. Let's write the equation. M3 minus M2 into L. That's the steam. It releases L when it changes the state. Then the same thing, now it's water. So CW into 100 minus theta 2. This is the total amount of heat released by the steam in both states. As the vapor state and the liquid state, this is the total amount of heat it has released. It is gained by whom? M2 minus M1. Or let's write M1 first. M1 Cc, that is the copper, the calorimeter and the stirrer together. M2 minus M1 is the water, Cw. Both of these have increased the temperature from theta 1 to theta 2. Shall we substitute? M3 minus M2. Let me calculate that here. M3 minus M2, 125.7 minus 124.1, which is 1.6. M2 minus M1, 124.1 minus 37.8, which is, we'll say if it is 40, it is 84.1 plus 2.2, 86.3. Double check. 11 minus 8 is 3. Then 13 minus 7 is 6. 11 minus 3 is 86.3 gram is the water. Steam 1.6. So M3 minus M2 is 1.6. L. CW 4200. We usually assume it to be 4200. 100 minus T2. T2 is 34 degrees. 34 degrees. Equals, I'll write it here. M1 C1. How much is M1? 37.8. 37.8. If you want, you can divide the M by 1000 to make it into kilogram. Then 37.8. But then even if you don't write the 1000, the answer is going to be same because everywhere you have M. So even if you don't write that by 1000, you're not going to get a mistake because 1000 you get in all three places get cancelled each other. Cc 400, copper it's 400. M2 minus M1, we have it here, 86.3 grams of water. Cw 4200, theta 2 34, theta 3 23, theta 1 23. This also I have to divide by 1000. All them. If you are dividing 1 by 1000, that means if you are converting 1 to kilogram, everything has to be in kilogram. If you keep 1 in gram, everything has to be in gram. Now let me leave all these thousands. 1.6 L plus 4200 into, this is 66. On the other side, 37.8 into 400 plus 86.3 into 4200 into, this is 11. 34 minus 23 is 11. Now, we are multiply, find this value and divide by 1.6. Right? The answer you get for that, when you calculate this and when you divide this by 1.6, the answer you get for that is 2.6 into 2.60 into 10 to the power 6. That is the answer you are getting for that. Relaxingly calculate and check. When you multiply all this and then divide by this 1.6 also, the answer you get is 2.6 into 10 to the power 6. Now you have to subtract this part as well. When you subtract that also, what you get is, this is 2.6 minus this, you get 2.32 into 10 to the power 6. 2.32 into 10 to the power 6. Latent heat, the units will be joule per kilogram, joule per kilogram. That means 1 kilogram of steam, when it changes into 1 kilogram of water at the same temperature, it releases 2.32 into 10 to the power 6 joule amount of energy, amount of heat. Similarly, 1 kilogram of water, when it changes to 1 kilogram of vapor, both at 100 degree itself, it consumes 2.32 into 10 to the power 6. The theoretical value we study is around 2.3 into 10 to the power 6, right? Because of the practical might have small errors, still we get a very close answer. 2.32 into 10 to the power 6 joule per kilogram is the answer we have got, right? So now you must have understood how we have done this experiment step by step, what are the logics behind each step, how we are reducing the errors here, all that you would have understood, right? Now what we will do, we will take some past paper questions on this, some questions that have been tested in this experiment, and see how to do that. Now let's see some past paper questions that have come from this particular practical. So this is from year 2000. They have given a diagram. The following diagram shows an arrangement made by a student to generate steam in the lab. Tube B is used to transport steam from the steam generator. Tubes A and B are incorrectly fixed in this arrangement. State how you would arrange them correctly. So look at this. Tube A. You know the purpose of tube A. Why is tube A kept? We want to maintain the external environment pressure and the pressure within the steam generator at the same level. That's why we keep that tube. But if you keep that tube like this, that means if this bottom end of this tube, if it is not submerged within the water, all the steam that is generated would be going out here. Whereas we want the steam not to go through that tube, we want the steam to go through tube B. Tube B. So how it should be arranged? You remember we studied right, if this is your steam generator container, if this is the water level, right, the tube that you keep for the pressure management purposes, the tube that you keep to manage or to maintain the internal pressure equal to the external environmental pressure, that should be submerged within the water. I told you, because when we do this, suppose if like when the water gets heated after 100 degree or at 100 degree, it becomes steam. When it becomes steam, it needs more space. Then because when the state changes, liquid state changes to gas state, it takes more space. Then the pressure will increase. When the pressure increases, to maintain the pressure same as the external pressure, the water will start going up in this, taking more space for it. Understand? By that means pressure will be maintained. And the other tube, you want to get the steam out of it, right? If you submerge it here, the steam cannot go through that. So the other tube, the tube that you keep for the exhaust of steam, should be kept such that the bottom end is not submerged within the water. It must be above the water level, then only the steam can enter into the tube. This way steam cannot enter into tube B. So what are the incorrect settings here? Tube A, they ask how you would arrange. So they didn't ask you the reason for that, how you would arrange. You say tube A should be submerged in the water. Tube B should not be submerged. Since steam has to enter into it. Right. So basically steam tube A must be lengthier so that one end is submerged within the water. Tube B should not be this lengthy. It must be lifted up so that it doesn't touch the water surface. Then it will have space for the steam to go through tube B. What is the necessity of having tube A? See, now only they are asking the reason. Why do you have tube A? Tube A to maintain the pressure within the steam generator the same as external pressure. So let's write that. To maintain the pressure within the steam generator at the same level of external or environmental pressure. Simple as that. Next one. After making the changes in A above, the student correctly inserted the end of tube B directly into the calorimeter C with water. Do you understand what he is doing? This is the steam generator. This is the tube for pressure management. So this is tube B. He brings the tube B and you have the calorimeter here with water. He directly fixes it here. See, he directly inserted the end of tube B into the calorimeter C with water. This step is not satisfactory. We can't do like that. Do you remember we used a steam trap in between? We used a steam trap in between. We didn't let the steam directly go and fall into the water. We used a steam trap in between. After the steam trap only the steam was allowed to go into the water. So they are asking, explain the reason for this. Why it is not satisfactory? Why it is not satisfactory? Why do you need a steam trap here? When the steam leaves from here, when it travels through this tube B, this is tube B. When it travels through this tube B, on the internal surface of tube B, some part of steam can get condensed and it can change the state into water. If we connect like this, the water, that means steam condensed and the water came from that, also will fall into the calorimeter with water. So when we get the final mass and subtract the previous mass, we are going to assume whatever the difference is totally steam, right? That assumption will be wrong because there is going to be some hot water as well into that. Understand? So let's write that. Let's write that. When steam travels through tube B, a part of it will condense on the tube surface, internal surface. The condensed water will fall into the calorimeter with water, into the calorimeter. So what error it will give? The mass of steam will be miscalculated. This will give an error in finding the mass of steam. Because we will assume all the steam, whatever the mass difference is steam, and the steam came into this calorimeter, then only it changed the state into water. So it has released the latent heat. But what happens here? Part of the steam has already released the latent heat and it comes as water. So our assumption and what actually happens will be different. Right? There will be an error in the experiment. In this experiment, before releasing the steam to the calorimeter, connecting another apparatus to the end of tube B is the correct approach. Draw the diagram of this apparatus in the space between tube B and calorimeter. So we'll go back to the diagram that they give. Right. The apparatus we used was like this. It had a curve like this. See, this is now the steam trap we used. What happens? All the steam comes here. Suppose if any steam has condensed here, the water drop also will fall here. But the water drop cannot enter into the other tube that goes to the bottom. Only the steam can go through this. So we can ensure only the steam that reaches the calorimeter. Whatever the steam that has already condensed, that is in the water state, liquid state, cannot reach the calorimeter. Apart from this, the steam trap, there is another format of steam trap as well. See, this steam trap is also acceptable. What happens here? Can you see? This is where the steam comes in. Suppose if any water is already there, that water will get collected here. Only the steam will enter into the other tube and from here we will get the steam. Can ensure the water, the steam that has already condensed, doesn't come out. But the mistakes you can do when you're drawing this, I'll show you the mistake that you can do. If you will draw like this, this is wrong. You know why that is wrong? You have kept both tubes directly under each other. So when the steam comes from here, suppose if any part of the steam is condensed and if there is water in that, that water is going to directly fall in this tube. So again, in this way you are going to get water as well, which is what we want to prevent. The whole purpose of having this steam trap is to ensure the condensed steam doesn't come out. So this way if you draw, it's wrong, it's wrong. I'll show you another wrong approach. This is also wrong. Why is this wrong? Why is this wrong? See, this tube, it has to be a little bit higher within that. Otherwise, when the water drops fall here, they can again come into this, right? Make sure this tube is a little lengthy within the steam trap, so that the water doesn't have a chance entering into the tube. Only steam will have the chance of entering into the tube. So if you draw any arrangements like these two, what is the mistake here? Both tubes are directly under each other. So water can fall into the next tube and come out. What is wrong here? The exit tube is not lengthy enough within the steam trap. So still the water can enter into the tube and it can come out. So these two are wrong. Either you can draw like this or draw like this. Both are acceptable steam traps. Yes? Next. What measurements would you take in this experiment other than the two relevant temperature measurements? Other than the two relevant temperature measurements. You need to take mass of calorimeter with stirrer. Make sure you write it with stirrer. If you don't mention stirrer, it's wrong because stirrer is also gaining heat there. It is also a copper stirrer. Mass of calorimeter stirrer and water. Mass of calorimeter, stirrer and water at the end. So this time it is not only the water that we kept already, the steam that condensed, that is also in. So the weight has to be higher. Here in this case, before the steam was sent. Now after the steam is sent. These are the three measurements that we have to take apart from the two relevant temperature measurements. What are the temperature measurements you need to have? When you are starting the experiment, what was the initial temperature of that calorimeter and water? When you end the experiment, what is the temperature of calorimeter and water? Those are the two temperature measurements you need. Which they did not ask, they said other than the temperature measurements. What additional data do you need to determine the specific latent heat of vaporization of water? You remember the calculation we are going to do? The heat released by water, released by steam, is equal to the heat gained by calorimeter, stirrer and water. Right? So what other calculations, what other parameters we need? Specific heat capacity of copper. Why copper? The calorimeter is usually made out of copper. Copper. Within brackets we can say calorimeter. Suppose if we are using a different calorimeter, let's say aluminium calorimeters are there. So if you are using an aluminium calorimeter, then it has to be aluminium here. Specific heat capacity of copper. Specific heat capacity of water. Water. Why? Water is also gaining heat. So when we apply MC delta theta, M we have already measured, C is required. C. What precautions can you take to improve the precision of this experiment? How can we improve the precision of the outcomes from this experiment? One, go back and see the arrangement. Right, in this arrangement, what are the precautions we can make here? One, we can keep a insulator here so that the heat doesn't get transferred from the burner to the calorimeter directly. Option number one. Two, we have to keep this completely lagged so that the heat emission to or heat transfer to the environment is minimized. Another, you can start the experiment around 5 degrees below the room temperature and finish the experiment 5 degrees above the room temperature, so that the heat gained from the environment, however you lag it, there will be some amount of heat transfer with the environment. So by starting the experiment 5 degrees below the room temperature, initially the system gains heat from the environment. Then when it goes above the room temperature, it releases heat to the environment. We can make an assumption both are equal. Right? So the heat gained from the environment, heat released to the environment will nullify each other. So that is another adjustment we can do. Let's write down one by one. Start the experiment at about 5 degrees below the room temperature and end the experiment about 5 degrees centigrade above the room temperature. above the room temperature. Point number 1. Point number 2, insert an insulator sheet between the burner and which one? The calorimeter. So that from the burner directly, if any heat is transferred to the calorimeter, that can be avoided. Calorimeter. Right? Those are the common precautions. Another one we can say, lag the calorimeter properly. If we lag it properly, we can ensure the transfer of heat to the environment is less, right? These are the common adjustments we can do. Next, when this experiment was done in a hill country school, the barometer reading was 720 millimeter. Usually, the atmospheric pressure, we assume it to be 760 millimeter. But you know that is at the sea level. When you go higher and higher from the sea level, the pressure reduces. So when you say a hill area, hill country school, then the pressure there, environmental pressure at the hill country is less. It's less. So what will happen when the pressure reduces? Water can boil easily. Because water boiling means thing like this. There is a glass of water, you are heating it. So the water, when it comes to 100 degree, the molecules, when they change the state from liquid to gas, they have to come out of it, right? And they have to start floating out of it. If the external pressure is higher, they have to work harder to come out of that external pressure. Imagine if I give 2 atm pressure, 2 atmospheric pressure, then the molecules can't come out easily. So they need more heat, more energy to push that pressure and come out. Similarly, if the pressure is less pressure on them, they can easily come out. Which means at in hill areas, the boiling point will not be 100 degrees centigrade. Even before 100 degree, at around 95, 96, 98, the water will get started to boil. Understand? We take an assumption the steam is at 100 degree. But if it is hill area where the atmospheric pressure is not as same as the sea level atmospheric pressure, because at sea level atmospheric pressure only we take it as 100 degrees centigrades. If the pressure is significantly different, see it's 720. What we usually assume is 760. Compared to 760, 720 is lower. So boiling point is not 100 degrees centigrade. It is something lower. We have to factor that in our calculations. Right? Which calculation? Steam's latent heat is okay. But after latent heat is released, steam becomes water. That water has to come to the equilibrium temperature, right? Suppose if equilibrium temperature is 35 degree, what we usually do is mc delta theta from 100 to 35 it comes. But in a hill area, that's not 100. So you have to take mc delta theta. You need to find out what is the boiling point for that pressure. Suppose if it is 95 degree, then you have to take mce 95 minus 35, not 100 minus 35. Understand? Right. So, explain how the student should consider this factor in his calculations. The pressure is lower than the usual atmospheric pressure. Therefore, the boiling point is lower than 100 degrees centigrade. The correct boiling point has to be identified. and used in calculating the heat released by the steam after condensing. To condense, it releases latent heat. That's fine. But after it condense, then it's water at high temperature. Maybe 100, 95, 98, somewhere. I need to know the right temperature of that. Right. Then only I can find out from that point to come to the equilibrium point how much heat that water would have released. Clear? Right. So, if the pressure is different, then we need to find out the boiling point. With that boiling point, we need to do the calculation. So, that's a good question at the end of this. Up to that point, everything was the usual steps. Last part, usually they include something for you to think and answer. And this is also not that difficult. Straight away, you know, pressure and the boiling point are connected. Everyone knows that. Right. So, that is from year 2000. Look at this question. This is from 2009 advanced level. The apparatus shown in the diagram can be used to determine the thermal conductivity of a metal in the form of a rod uniform cross section. In this experiment, steam at 100 degrees centigrade is passed through the chamber and the temperature theta of the water in the calorimeter is measured with time t. Let's try to understand. This is not the usual experiment we do or we have done, but we'll try to understand. See, this is the chamber. They are sending the steam through this and they are getting it out here. Steam goes in, it comes out. Steam goes in, it comes out. And they have kept a metal rod of constant or uniform cross section. Thickness doesn't change, same thickness. They have done the lagging, insulated properly. And where this rod goes, it goes into a calorimeter which is filled with water, and this is in touch with that water. And there is a stirrer to keep mixing this water. Calorimeter has been closed with a lid, and there is a thermometer also. Right. I understand the diagram. What will happen now when they send the steam? You know, water might be at the room temperature. If it is room temperature 30, the water might be initially at 30. When we send the steam here, this end will get heated. Right? This end will get heated. Close it, like with time, it will become 100 degree. Then what will happen? The heat will get transferred this direction. Heat will get transferred this direction. Right here, the heat will get transferred to the water also. So, water initially which was at the room temperature will start getting heated now. Right. So, what they do, they measure the temperature of this water with time. With time, how it increases. They are going to give a graph for that. Let's see. Give reasons as to why steam is always used in this type of experiments. Why do we use steam there? Why can't we just take the rod and heat it up with a Bunsen burner? You can't be sure about the temperature. If it is steam, we know for sure it's 100 degree. If it is steam, because if it falls below 100 degree, then it will change the state into water. And when we are generating the steam, if we ensure the environmental pressure is at 1 atm, at 100 degrees the steam will start getting generated. Right. If you keep the pressure more, if you don't let the steam to come out, then it will go beyond 100 degree. But if we had the arrangement set up properly, at 100 degree the steam will start coming out. So, it will not be below 100 degree, it will not be above 100 degree. It's easy to maintain 100 degree with steam. Understand? So, Give reasons as to why steam is always used in this type of experiments. Since it is reliable to maintain the temperature at 100 degrees. At 100 degrees. Otherwise, you can even heat it. You can burn, like with the Bunsen burner or some other source, you can heat it on one side. But there is no guarantee about the temperature. But if it is steam, you can always maintain at 100 degrees. The variation of the above mentioned theta with T is given below. Can you see? Initially, the theta is increasing at a higher rate. And then slowly the rate decreases. Can you see? Initially, the graph is steeper. Right, with time, it becomes more and more flatter. It's a curve. It's a curve. According to the graph, after t equals t1, theta attains a steady value. What is the reason for this? That means the graph has become constant after this, after t1. What's the reason for that? What do you think? What do you think? Now see, the calorimeter is here. The water gets heated. Then what will happen? Calorimeter and water will be losing heat to the environment. Can you see the calorimeter is not lagged here? It's not insulated. So the heat will get released to the environment. So what? Then what will happen? The heat that is transferred into the water and the heat that is transferred from the water to the environment, the heat that comes in and the heat that goes out will become equal at a point. Let's try to understand how that becomes equal. Why didn't that become equal initially? Initially, look at this. Look at this. It is always at 100 degree. Initially, it's at 30 degree. Room temperature 30. So, look at the temperature difference. 100 minus 30, 70. Since the temperature difference is high, more heat will get transferred. You know, heat transfer is proportionate to delta theta by the thickness. Delta theta by thickness. Delta theta means the temperature difference. So, when the temperature difference is bigger, more heat will be transferred. Heat transfer will be at a faster rate. Right. This is thickness. T is thickness. What will happen slowly when the water gets heated, this 30 will become 40. 40 will become 50. Little by little, when the temperature of this water increases, then the heat transferred into the water will reduce. Right? So, there are two things. Now, look at this. Right? It gets heat. Let's say that is H1. It releases heat, H2. Now, let's analyze H1 and H2. Let's analyze. H1 is proportionate to, if I take the temperature here as theta, 100 minus theta over thickness. Thickness doesn't change, no? 100 minus theta. Whereas H2 is proportionate to the room temperature, let me take it as 30 degree. So, theta minus 30. Right? Now, look at this. Initially, when theta is also 30, there is no heat transfer outwards because theta is 30, external environment is also 30, no heat transfer. This will be high. Why? 100 minus 30 is 70. The temperature difference is big. A lot of heat will be transferred. Now, when theta goes to 40 degree, what will happen? This will increase slowly. Why? 40 minus 30. Compared to the environment, now the water within the calorimeter is having some temperature difference. So, slowly it will start releasing heat to the environment. Now, earlier we had 100 minus 30. Now, it is going to be 100 minus 40. Now, still it gets heat, but not at the rate it was getting earlier. Why? the temperature difference in the rod is reducing. Earlier it was 130, now 160. Temperature difference has reduced. When theta goes to 50, this will further reduce, this will further increase. So at some point, H1 and H2 will become equal because H1 keeps falling. But H1 means what? The rate at which heat is transferred into the water. H2 is what? The rate at which heat is transferred to the environment. H1 keeps falling. H2 keeps increasing. At some point, they will become equal. They will become equal means what? The heat transferred into the water and the heat transferred to the environment, both are equal. Which means the water doesn't retain any heat for it. It gets it, it releases it. It gets it, it releases it. Then the temperature cannot increase. Understand? That's what they're asking. How comes that comes to a equilibrium, a steady state? Then we can say the heat at which the rate at which heat is transferred into the water and the rate at which heat is transferred from the water to the environment are equal. From the water to the environment are equal. That's why the steady state is obtained. From 0 to t, the way t1, the variation of theta with t is non-linear. Non-linear means it's not a straight line. Linear means a straight line. Non-linear means it's a curve. You can see it's a curve, yes. Non-linear. And there are two main reasons for this. What are they? Two main reasons. One, initially the heat transferred in is at a higher rate. Later it is at a lower rate. So the rate at which heat is transferred in reduces because of the temperature difference reduces. Similarly, the heat loss is also increasing. Initially heat loss was low. Now heat loss is increasing. Those are the two reasons. Why? Like initially we see we are increasing at this rate. Later the rate reduces. That means the water's temperature rising rate reduces. That means the heat at which water gains heat, the rate at which water obtains heat reduces. Why it reduces? Transferring in, the rate at which heat is transferred in reduces. At the same time, the rate at which the heat is lost to the environment increases. Income reduces, outgoing increases. Both will have a declining impact. So let's write it. Two reasons. What are they? One, when, or without one we'll say, with time the temperature of water increases. Temperature of water increases. With time, the temperature of water increases. Therefore, this will lead to one, a decline of the rate at which heat is transferred in. Due to declining temperature difference. That's point number 1. Point number 2, increase in heat loss to the environment. As temperature difference increases. Right, temperature difference increases. Let me explain once again. See, this is water, right, theta. It gets heat from a source where it is at 100 degree, 30 degree. It loses heat here. When theta increases, what will happen? When theta increases, the rate at which heat is transferred in will decline. Incoming heat declines. Incoming heat declines. At the same time, outgoing heat, the heat loss increases. Incoming reduces, outgoing increases. So the heat retained here, temperature difference or temperature rate at which temperature increases, that will decline. It will not, temperature will not decline, but the rate at which temperature increases will decline. Initially it was increasing faster, now it will start falling slowly. The rate at which it increases will fall. After some point, the temperature will not increase. Next, what is the temperature achieved by water at the steady state? Let's see the steady state temperature. Steady state 60 degree centigrade. It has been found from a separate cooling experiment that the rate R of heat dissipation from the calorimeter and its contents at temperature theta is given by R equals 0.16 theta minus theta R, where theta R is the room temperature. Calculate R at the steady state temperature. Simple. They say the rate at which heat is lost to the environment is given by this equation. 0.16 theta minus theta R, steady state theta was 60, room temperature is 30. So this is 30 into 0.16 is 4.8 joules per second. Yeah, joules per second. That's the rate, right? That's the units of it. 4.8 joules per second. In watts, yes, in watts. Hence, determine the thermal conductivity of the metal. Cross-sectional area of the rod is 1.2 into 10 to the power minus 4 meter squared, and the length of the rod from P to Q is 0.4 meter. So you know, at steady state, R in is equal to R out. That means the rate at which heat is transferred in is equal to the rate at which heat is transferred out. That's why steady state. R out we have got 4.8. R in, let's use this formula. Now look at this. We have a rod. We have a rod which has a cross section. A. This is the thickness because heat is transferred in this direction. So this is the thickness, right? Here it is 100 degree. Here it is theta changing. But theta is 60 degree. At steady state, it stays 60 degree. A is given, thickness is given. Right? So you know it's K A theta 1 minus theta 2 over thickness. K A cross-sectional area 1.2 into 10 to the power minus 4. Theta 1 minus theta 2, 100 minus 60. Thickness 0.4 meter. Right. All are in the correct units. So that will be K will be equal to 4.8 into 0.4 divided by 10 to the power 4, I will put it up, 2 into, or 1.2 into 100 minus 60 is 40. So we can solve it. 4, then 4, 10, 1000, 0.4 into 1000 is 400. 400, this is watts, right? Watt. On this side, this is meter squared, this is meter. So 1 meter will remain, m minus 1, Kelvin minus 1. Understand? 400 watt meter minus 1 Kelvin minus 1 would be the answer. Very simple. See, this is the cross sectional area. You need to find from where to where, in which direction heat is getting transferred, because that will decide what you are going to take as cross sectional area and what you are going to take as thickness. So in this rod, heat goes in from this end and it gets dissipated from the other end. So this is the thickness. You have to take this much as the thickness, the distance through which heat transferred. There will be a temperature gradient here. Temperature will keep falling here. And this is the cross-sectional area, which is uniform. They said it doesn't change. They have given A, they have given thickness, they have given the temperature difference, only K is missing. You know, Ka delta theta by T is the heat transfer rate. Use that and find K. If the calorimeter is also lagged well, could you perform the experiment successfully? Explain your answer. No, imagine if the calorimeter is fully lagged, then there won't be any heat transfer to the external environment. If there is no heat transfer to the external environment, the steady state will not be achieved easily. Steady state will be achieved when the water becomes 100 degree. Then 100 degrees the steam, 100 degrees the water, then there is no temperature gradient between the steam and the water, so that there is no heat transfer. But it will take a lot of time. It will take a lot of time. Understand? So it's pretty hard. If there is no heat dissipation to the environment, doing this experiment will be hard. So let's say, could you perform the experiment successfully? No. If the calorimeter is lagged, there will be no heat loss to the environment. Then the steady state will be achieved only at 100 degree. This will take longer time. And can't find K. Because you have to find K, you said heat transferring in, heat transferring out, both are equal. Using that equation only we found K, right? So if there is no heat transfer out, what equation are we going to use to find K? Therefore, if it is completely lagged, then you cannot find K. Clear? They ask, can you do it successfully? No, you can't do it successfully. First you have to say no and then explain your answer. So somebody who did not know how to explain, at least if you wrote this no, you get half of the marks. To say no, they give marks. And to explain some other marks. Right? Look at this one. This is from 2014. Another question. Slightly different from the same concept that we studied. Slightly different question it is. Let's see. An experiment is to be designed and carried out to find the specific latent heat of vaporization of water using an electric method. Wow, let's see what this electric method is. The labeled experimental arrangement of the items to be used for this purpose is shown in figure 1. Looks interesting. We'll see what it is. They say this is digital thermometer. Where is it connected? They have a silver plated double walled vacuum container. Basically a properly lagged container. There can't be any heat conduction because there is vacuum in the middle. See, in between this gap is the vacuum. Electric immersion heater. Don't worry about the terms. This is the usual heater that you use at kitchen. Right, you take a cup of water, you keep the heater and you boil the water. Same thing, but they have some fancy names. Electric immersion heater. Thermistor. What is thermistor? Thermistor, we studied. Thermistor, it changes with, like, the resistance of it changes with temperature. Right? When the temperature increases, its resistance reduces. So what they are going to do here, they are going to fill this with some liquid and they are going to heat it. See, that's connected to 240 voltage. That's the normal power supply at home. Then the water will get heated. Water, the liquid will get heated. When the heat increases, this thermistor's resistance will change. Resistance decreases. Based on the resistance, this digital thermometer will measure the temperature. Right? Simple. The resistance of thermistor and heat, there will be a graph. So if you know the resistance, you can find the temperature. That's what the electric so-called digital thermometer is going to do. Electronic balance. That's nothing much. You just keep anything on that. It shows the mass of it. Nothing much. Digital stopwatch. Digital stopwatch. You start and stop. You can see the time. Cool. That's the arrangement. Though the arrangement looks very fancy, there is nothing much in depth there. Quite straightforward arrangement. If at all you might have forgotten this thermistor. Thermistor. In electricity, we would have studied thermistor. You would have forgotten that. Apart from that, there is no complication here. Experimental procedure. Even that they are giving it. Nice. Add a sufficient quantity of water to the silver plated double walled vacuum container which is kept on the electronic balance. This is sufficient quantity. Sufficient quantity. Okay. What do you think the sufficient quantity would be? They have marked two lines here. Let me say this is A, this is B. What do you think? Should we fill up to A or should we fill up to B? I mean, general practice, if you have at least visited your kitchen once in a while, if you are using this heater, we usually fill water as much as possible. The reason what your mom would say at home is to prevent this heater from burning. If you half fill the water and keep it, it might get burnt. Right, so it's a common sense. People know that water has to be filled as much as possible. The entire heater has to be submerged or immersed into the water. Another reason we are going to say here, now the heat that is generated by this heater, if you don't submerge it fully, let's say you submerge it half into the water and half is exposed to the environment, then half of the heat is going to the environment, right? Your calculations will be wrong. You assume all the heat goes into the water, but you have kept half of it open to the environment. Then half of the heat is dissipated to the environment, which we don't know how much. Understand? So if you want to take an assumption, all the heat generated by this heater is given to the water. If you are going to take that assumption, make sure you fully submerge it or you fully keep it within the water. Yeah, so level A must be the right level to keep water. Don't put up to the brim. Then what will happen when the water is getting heated? It might drop outside. Then that will have problem with your mass measurements and all that. Don't put too much as possible, keeping some space, because when the water boils, there will be bubbles coming out. It should not result in dripping of water from this, right? So just have some common sense about it. Switch on the electric immersion heater. After the water has started boiling thoroughly, at the boiling point, start the digital stopwatch. At the boiling point. So wait until water boils. You can see the water will start dancing at the top, like the bubbles will come out, right? Stopwatch at a certain instant. After that, you switch on the stopwatch and also record the reading of the electronic balance at that instant. Okay, when you are switching on the stopwatch, check the electronic scales measurement also. After a suitable time t, record the reading of the balance again. So what happens when the water is boiling? Now it has already started boiling. Then the evaporation will happen, right? Water will little by little will start evaporating from the calorimeter. So the mass that is shown in the electronic scale will slowly fall down. So after 5 seconds, 10 seconds or 20 seconds, when you check the mass, it has to be lower than what it was earlier. Because of the water getting boiled and vaporizing. If several readings for M1 are needed, continue the experiment without stopping and record the successive readings of the balance set times 2t, 3t, 4t and 5t. That means if you want to draw a graph, suppose earlier if you have taken at 20 seconds, you again take the mass at 40 seconds, 60 seconds, 80 seconds, 100 seconds, so that you can draw a graph, time versus mass. Yes. When the experiment is carried out, right, wait. So before we go to the question, we'll try to understand what are they trying to do. They want to find the specific latent heat of vaporization, right? They are measuring the time. They are measuring M of steam they can measure because they know the initial mass. After some time, they know the mass that remains. The difference would be the steam that has been generated. You are starting this when the water started boiling. So it's already at 100 degree. Already at 100 degree. Only thing happening at 100 degree, some water is getting vaporized. Right. Then, in this time t, can I say heat transferred in should be equal to heat transferred in should have been used to do what? To vaporize that water only. There won't be any rise in temperature because when you started the stopwatch, already the water was at boiling point, which means it's already at 100 degree. It doesn't increase further. So I don't have to put MC delta theta, that's over. After that only you are starting the stopwatch. Still the heating happens. So where does the heat goes? For the change of state from water, from liquid to gas, which is what you call latent heat. Then I can say heat in must be Ms into L. Ms we can find it because we know the mass difference. L is what we are going to find. This is an immersion heater. You can find out how much of heat it would generate. It would, if we know the power of this, we can find how much heat would have generated in the time t. Right? We can use all that and find L. This is what they are trying to do. Interesting experiment. Heat given by this immersion heater is used only for the latent heat. Why do I say only for the latent heat? We started measuring the mass, we started measuring the time only after water came to the boiling point, which means it's already at 100 degree. From 100 degree, what happens? It gets vaporized. When the experiment is carried out according to the above procedure, suggest up to which level A or B marked on the diagram should the water be filled. Give 2 reasons for your choice. Assume that when boiling, water does not spill over the container. Spill over the container. So we already have marked it must be at level A. Why? Reason number 1, to ensure that the heater is fully submerged in the water such that all the heat transferred, all the heat produced, all the heat generated is transferred to the water. and not to the environment. Not to the environment. Because if you keep half in, half out, from the outer part of this heater, whatever the heat generated, it's going to be going to the environment. Then you can't talk about this equation where I said heat in means heat generated, right? Heat generated is used for M into L. You can see only if all the heat is given into the water. Second thing, another thing I can see, if you keep the water at this level, imagine, okay, when you are heating it, the evaporation happens at 100 degree, right? Some of these evaporated water, that means now it's gas, it's steam, it might hit this wall of this container, and it might get condensed there. Because if they meet a surface, they might get condensed there. Then again they are going to fall into the same calorimeter. Which means it already took the latent heat and came out, but it did not come out fully. It again falls into the calorimeter. So the mass difference, what you are going to take as ms, is going to be wrong because it has again fallen down. It has again fallen down. So the mass of steam that you are going to find would be actually less than the steam that was generated. Part of the steam again fell in. So it will not be reflected in the mass calculation, right? So you should not leave too much of space open, because the steam might go touch that surface, get condensed, and again fall into the same calorimeter, same container. To avoid that, we will fill as much as possible. So another reason we can say, to minimize open internal wall of the container, because the steam may condense on the internal walls of the container, resulting in errors of mass of steam. In finding the mass of steam, that will be an error, right? Because all the steam that has been generated should come out of the container. Then only that will be reflected in the mass. If it again falls into the container, it will not be reflected in the mass. Next, how does the silver-plated double-walled vacuum container reduce the heat loss? How does the silver-plated double-walled vacuum container? So one thing you can see, silver-plated, right? Since the surface is polished or silver-plated, radiation is prevented. Vacuum helps to prevent heat conduction. There are only three methods of heat transfer: conduction, convection, and radiation. Conduction and radiation will be prevented by these two. Shiny surface prevents radiation. Proper lagging or keeping vacuum in between will help you prevent conduction of heat. Indicate which property of the thermistor is used to measure the temperature, and state how this property changes with temperature. Did you understand? There are two questions in this. They are asking which property and how it behaves. So first let's say which property. Thermistor, I already explained you. What is it? Resistance of thermistor changes with temperature. Resistance of thermistor changes with temperature. Then how does it change? When temperature increases, resistance decreases. That means negative relationship or negative correlation. Negative correlation between resistance and temperature. Next, if P is the power of electric heater in watts and T is the time through which the water has been boiled off as steam, write down an expression in terms of PT and the measured quantities M0, M1 under the experimental procedure. So I told you heat given in. Heat given in means P is the power. Power means watt. Watt means joules per second. It was giving heat like that for T seconds. P into T. This is the heat transferred in, and that was used for what? For the 100 degree water to change into 100 degrees steam. So it has consumed the latent heat. M0 minus M1. M0 is the initial mass of water. M1 is the end mass of water. End mass is less because some water has evaporated already into L, where L is the latent heat of, all these are given, P, T, M0, M1 given, L we have defined. Latent heat of vaporization of water. Next, if the least measurement of the electronic balance is 0.1 grams, what should be the minimum mass of water that has to be boiled off to ensure that the frictional error in the measured mass of water fractional error had been boiled off as steam is 1 by 100. The error has to be 1 of 100. Right. That will be 0.1 divided by M0 minus M1. So M0 minus M1 has to be 10 grams. 100 into 0.1, 10 grams. M0 minus M1 will be 10 grams. Next, if P is 500, calculate the minimum time of T through which the water has to be boiled off in order to satisfy the requirement given in E above. So what we got in this answer, so here we got the answer as 10 grams, right? So what that means is the difference in mass we get if it is less than 10 gram. Let's say you have got 5 grams. In 5 grams, suppose if there is 0.1 gram error 0.1 is possible. 0.1 out of 5, how much is that? If you multiply up and down by 0.15, if I multiply by 2, 0.2 by 10, it's 1 by 50. 1 by 50. Straight away I could have multiplied by 10 up and down, 1 by 50. But they want error to be 1 by 100. So this is a bigger error than that. 1 out of 100, 1 out of 50, this is a bigger error. So the mass you measure, the difference, the mass of steam that you measure should be at least 10 gram to ensure that the fractional error is 1 by 100 or more than that. Imagine if this is 20 grams. 20 grams in 20 when you get an error of 0.1, that is 1 by 200. 1 by 200 is a smaller error than this. 1 by 100 means 1%. 1 by 200 means 0.5%. Small error. That's why we say at least 10 gram has to be the mass of steam. Now they are asking, okay, if the steam generated has to be at least 10 gram, how much time it needs? Because if you finish the experiment too quickly, 10 gram steam would not have been prepared or generated. So how long would it take to generate 10 gram of steam? So we already have the formula. P into T is ms, let's say, into L. P is 500 watts. T. ms has to be 10 gram, 10 by 100, 10 by 1000. To change that to kilograms. 2.3 into 10 to the power 6. So now you see 0, 0, 2 zeros, 10 to the power 4. Then 3 zeros, 10. Check that, check that. T, ms into L, this is joule per kilogram. Yes, 10 grams. We got 10 grams. So change that to kilograms. Right. So T we are getting 2.3 into 10, 10, 230 seconds. 230 seconds. So at least 230 seconds you have to keep. 230 seconds means that's actually 3 minutes and 50 seconds. 3 minutes means 180. 3 minutes and 50 seconds you have to keep to get at least 10 gram of steam to be generated. Why at least 10 gram? Then only the error percentage will be less than 1 by 100. Next. A graph of mass m in grams of the vaporized water with time t was plotted using the data taken under the experimental procedure number 5. And the coordinates corresponding to 2 points on the graph are there. Determine the value of L. Let's first analyze how the graph is going to be. P into T is graph of mass m in grams. Okay. M into L. So M will be P over L into T. Y equals mx. Can you see? So the gradient will be P by L. Gradient will be P by L. But the problem is they have taken that in grams and minutes. But we have to use it in kilograms and seconds. We'll do it carefully. Look at this. P by L. Gradient. Gradient will be 106 minus 26. Change in Y by change in X. But careful, change in Y. Y is what? Y is M. M is in grams. Multiply by 10 to the power minus 3 to convert that to kilogram. X is what? X is time. Time is in minutes. Multiply by 60 to convert that to seconds. Convert that to seconds. Now, P is given 500, right? 500 over L. This is 80. 10 to the power minus 3. 6 into 60. So L will be, L goes up there. So I can take 6 into 60 is 360 into 500 divided by 80. 10 to the power minus 3 will be 10 to the power 3 on the other side. That will be, if I take these 3, that will be 10 to the power 6. Then 5 and 36. 5 and 36 is 180. 180 over 80 means 94. 2.25 into 10 to the power 6. 2.25 into 10 to the power 6. What is that? Joule per kilogram. Joule per kilogram. Careful, here you should have converted the grams into kilograms. Time they have given in minutes, that you should have converted that to seconds. Otherwise, you wouldn't get in these units. You will get some complications. So, better thing, always convert that to kilograms and seconds and then do it. You will get the answer comfortably. Again, see what did we do? This is the formula we already had. Power into time equals mass of steam into the latent heat. Mass is what you take in the y-axis. T is what you take in the x-axis. Because you give more and more time, the mass is going to be higher. So, T is the independent variable. M is the dependent variable. M depends on T. The mass of steam depends on how much time you are heating it. So, independent variable comes in the x-axis. Dependent variable comes in the y-axis. Then, the gradient is going to be P by L. The points they give 8 and 106, 226. So, delta y over delta x, change in y, change in x. But change in y comes in grams, multiply by 10 to the power minus 3 to convert that to kilograms. Change in x comes in minutes, multiply by 60 to convert to seconds. P was given in the previous part as 500. Keep doing it, you get the answer. Understood? Right. So, see, there was, like, I have done 3 questions. One was directly from the experiment we did. Same experiment, same diagram, they had questions, which is straightforward. The other 2 are modified experiments. We did something with similar concepts, with similar ideology. They did some different experiments. So, don't be surprised if you see experiment related questions where the experiment is not the same that you did in the lab, slightly modified. Then, read the data carefully. They would have given you all the instructions. See, this experiment, they have given even the instructions. This is how we do the experiment. So, read it, understand what happens in the given experiment, and then do answering the questions. Clear? But to do whatever, proper understanding about the experiment we have done is essential. Spend enough time, go through at least couple of times how we do the experiment. I give explanation at each point. Why am I doing this? Why am I doing this? Go through all that and then understand, come and do these questions. What you get in the exam will be so simple for you. Practice this. We'll meet up with another experiment soon.